Okay, so this work, this is the work and we talk about is just like we've just put it on archive, so and we haven't submitted it yet, so you can, if you have any comments, like that would be really welcome. So this is a joint work with Tomasz Waszkiewicz, who's a PhD student at Oxford, and Nikita Zhivotovsky, who's currently a postdoc at ETH Zurich. Okay. So I'm going to start by presenting the setting. Okay, so we will be looking at a problem of a statistical learning problem or prediction problem, where we try to predict a value of interest y, an output, based on some variables, some covariates x. So these are like d variables, so which constitute a vector in RD. And this is the input, and given the input, we want to predict the output. And of course, we are in a statistical setting, so there is a relationship between the two, which is encoded through a joint distribution on the pair. So we assume that the pair xy is a random variable with some distribution, joint distribution on RD times R. And the reason why this is a statistical problem is that the distribution of the pair is unknown a priori. Okay, so now now that we have distribution, you can define the prediction error of a prediction function. So prediction function just takes covariates x, and they map them to a prediction f of x. So they map input to predictions. And we will consider an error which is a squared error. So the error is the squared of the difference between the prediction and the outputs. So it's and the risk is just the expected squared error. So it's the standard measure in regression. And the class of functions, so we consider a class of functions, which is composed by the class of linear functions. So all linear functions which are parameterized by a parameter of coefficients W in RD. Okay, now I can state the formal statistical problem we look at. So we have some IID sample from the distribution. And given this IID sample, independent and identically distributed sample from the unknown distribution, we want to find a good prediction function. And formally, this means a function f hat, which depends on the data. So I will call it a procedure or an estimator, which has small excess risk. And what do I mean by that? So I mean that the difference between the risk of my prediction function and that of the best linear function is small. So basically what this means is that I'm trying to find a function whose prediction error is at least as good, almost as good as the best linear function. Okay, so this is the setup. And I will start with some basic facts, just to be just some reminder. Okay, so we can define the class of linear functions, and if we have some enough assumptions, we know that there is a risk minimizer. So I will assume now that the covariance matrix sigma, so the expectation of XX transpose, so that this matrix is invertible without loss of generality, and this matrix, it encodes how the data X varies in different directions, basically, of the space. And I'm going to assume that it's invertible, and in this case, there is a unique minimizer of the population risk, of the true risk. And if it's not invertible, it's almost the same. So there is an affine subspace of solutions. Okay, and now if you have a linear function, we can look at the difference, its excess risk, so the difference of its risk and the one of the best linear function. And because the class of linear function is a vector space in L2, we can have like Pythagoras theorem. So we know that the excess risk is the L2 distance, squared L2 distance between the two functions, two linear functions. And so the excess risk is just some quadratic form of the difference of the two parameters. And the difference is encoded by the covariance matrix sigma. Okay, so So since we don't know the distribution P, so we don't know the population risk minimizer, this is what we try to approximate. But what we do have is that we have an IID sample, and from this IID sample, we can define the empirical risk, so it's the average risk on the sample that we have. And the most natural estimator, the most current one, the most common one, is the empirical risk minimizer. So you just minimize the empirical risk over all the linear functions. And it's also called the least squares estimator because it's the solution to the least squares problem. And it has an explicit expression given by this one. So compared to the population risk minimizer, you just replace the expectations by empirical average over your samples. And in particular, it depends on this object, which is the empirical covariance matrix, which is the empirical analog of the population covariance. Okay. So I will now survey quickly with a quick survey of existing results in this setting, like some kind of things we can do. Okay, so we can take the best parameter, and I can define, given this best parameter, the error, which I call Xi, which is the difference between the prediction of the best linear function and the true value Y. And okay, and I had some expression both for the excess risk and for the least square solution. So the excess risk of the least square solution, it has this expression here where I have multiplied by sigma. And I can split it in two terms, basically. There is a vector here, so this vector here, and some like matrix here. And the vector, you can interpret it as a noise term. It's basically the spurious correlation between the errors on your sample and the linear functions or the covariate vectors. So this is a classical term, even that you have even in the fixed design case. And then there is another term, which is the one which is specific to the fact that we look at a problem, which is a random design problem, which means that we try to predict on a new sample. And this is basically, it's some sort of, it's related to the fluctuations of the empirical covariance matrix around the true covariance matrix. So if, at least asymptotically, like if n goes to infinity, this would, like this matrix here would go to the entity, and so this factor would tend to 1, but it can be, typically it can be also much larger, depending on n and the distribution. Okay, so now if we want to try to analyze the performance of least squares, we have to account for both of these terms. So I will go a bit quickly, but basically there is one type of analysis, which is the analysis of least squares under strong assumptions on the distributions. And so typically the assumptions would be that the distribution of X has some boundedness condition like this, or that it's sub-Gaussian. And what I mean by sub-Gaussian is not super important, but basically it means that the one-dimensional projections would be bounded in terms of the ones of a Gaussian distribution with the same covariance. Okay, so these are both like quite restrictive assumptions, especially in high dimension. But the reason they are helpful is that they enable to control like the matrix term in particular, which is the hard term often, and they imply some form of matrix concentration. And concretely, what it means is that for n larger than d, or d log d, the empirical covariance matrix would be of the same order as the true covariance matrix, so the covariance term will be controlled. And what this means is that if the errors are also light-tailed, so like sub-Gaussian, then we know that the ordinary least squares solution will achieve the optimal bound, which is d over n. Okay, and the intuition between this phenomenon is that it's really related to the concentration of measure. So what this says is that essentially all the empirical risk, so the risk on the sample, would be close to the risk on the true risk. And so the function which have a good risk, a good population risk, good true risk, will also have a good empirical risk and vice versa. So in particular, the empirical risk minimizer will be close to the true risk minimizer. Okay, and I put here some references in the specific case of linear functions, but this is really a standard approach. Okay, so there is a more recent line of work, which is about analyzing least squares under weaker assumptions. So now I no longer make the strong boundedness assumptions, and instead I relax them by weaker assumptions, so only finite moment assumptions. And this takes the form of that I put here. It's not extremely important, but it's some form of control of moment ratios. So basically what this says is that the fourth moment of one-dimensional linear projections of X in all directions. So these are always larger than the L2 norms, but now I ask that there is a converse inequality. So that the L4 norm is controlled by a constant times the L2 norm. And what this means is that basically in no direction, you can have a variable Wx that takes very different values at very different scales, basically. Okay, and this type of condition was introduced in the literature by Oliveira. And it's also related to another assumption, another moment equivalence assumption, which is even weaker, which is called the small ball assumption, which was introduced by Kolczynski and Mendelssohn and Lequet and Mendelssohn. And okay, so these assumptions are weaker than the sub-Gaussian conditions on X, and they don't imply matrix concentration as before, but they imply something weaker, which is just a one-sided bound. So we just know that the empirical covariance is at least as large as the population covariance, but it can also be much larger. And if you remember the equation I showed, basically it only depended on the smallest eigenvalue of the ratio of the two. So actually this is enough to control the excess risk. So we don't need matrix concentration, we just need a one-sided bound to control the risk of ordinary least squares. And so the intuition is that basically this condition, what it gives, so it doesn't show that it's not enough to imply that the empirical risk is close to the population risk. So this is no longer true. But it implies that the functions which have a bad risk, a bad population risk, will also have a bad empirical risk. So they will also be bad on the data. And since the empirical risk minimizer is the one with the smallest empirical risk, it cannot have a large population risk. Okay, and so in particular, if the error is well behaved, this is enough to show that we have a D over N bound with least squares. But there is also another case, which is the case where the error is heavy-tailed. So now both X and the error are heavy-tailed, so they are not sub-Gaussian. And in this case, one can show that empirical risk minimization will no longer be optimal. But there are some alternative, more sophisticated procedures, some robust estimators. And robust here refers to the fact that we have heavy tails of the errors. So some sophisticated estimators will achieve the D over N bound. And so this was a line of work which was initiated by Audibert and Catoni and put some other references, Lucosier and Mendelssohn, as well as Catoni. Okay, so just to summarize, I gave a bit of an overview. So there are different types of conditions on the distribution of X under which we can get guarantees. There are strong assumptions like sub-Gaussian. There are weaker assumptions like these moment ratio conditions. And they are weaker than the previous ones, but they are still non-trivial. And they are not always satisfied, and there are cases where they can lead to bad bounds because the constants can depend on the dimension. Okay, so the question we will consider now is that is whether we can actually remove any assumption on distribution of X. So not just weaken it, but in fact remove any condition. Okay, so this is so now we'll introduce formally our setting. Okay, so to define our setting, I have to make some definitions of what we mean. And I said distribution free, so I have to say what I mean by distribution free. So formally, we have a joint distribution of the pair X and Y. And this joint distribution is characterized by two things. So the first one is the distribution of X, the marginal distribution of X, which is a distribution on RD. And the other thing is the conditional distribution of Y given X. And so this is a family of distributions of Y, so on R, indexed by values of X, indexed by values of X in RD. So for each X, we have the conditional distribution of Y given that X is equal to small x. And if we know this, we also know we can also define the best prediction function among all functions, which is just the conditional expectation, which I call the regression function. And now I will say that a bound or guarantee is distribution free. And so this is what I mean by distribution free. If it holds for all distributions of X, so without any assumption on X. And so now the two questions, the main questions that I will talk about are, the first one is whether it is possible to obtain some distribution-free bounds at all. So the ones I showed before were not distribution-free. And the second one is, if so, what conditions do we need on the conditional distribution of Y given X? So this is our setting. So I will answer by anticipation the second one straight away. So our main condition on the conditional distribution of Y given X is bound on the conditional second moment of X. So the condition says that there is a constant m squared, which is such that for every X, the conditional expectation of Y squared given X is equal to X is smaller than m squared. So this will be our only condition for the rest of this talk. And so this is a condition which is always satisfied when Y is bounded. So when Y is bounded by M, this is obviously true. But it's also a much weaker condition because it doesn't require boundedness. It's actually a condition only on the second moment, conditional second moment of Y, sorry. And in particular, you can have, it's compatible with a variable Y, a response Y, which has heavy tails. And in particular, it may even only have 2 moments and not even more than 2 moments. Okay, and we will. So I will not show a precise statement saying that in the talk, but basically one can show that this is really a minimal assumption on the conditional distribution if we want to have any interesting distribution-free guarantee. And there are lower bounds, but I will not show them here. Okay, so I will start by considering a class of estimators, which is a natural class. So I will say that the procedure is proper or linear if it always returns a linear function. Okay, so this is so I want to compete against the best linear function, and so it's actually natural to return a function in the class I try to approximate. And many procedures are like that. This includes the least squares, but also many of the procedures in the literature, including the ones I mentioned before. So the robust ones are actually, they return linear functions. Okay, and so I'll start by some bad news, which is that if we have any linear procedure, and this is a result which is essentially a consequence of a direct consequence of a result by Shamir. So if we have any proper linear procedure, we can find a distribution of P of X and Y such that Y is bounded by 1. But on the other hand, the excess risk of this procedure is at least it's of constant order. So it's lower bounded by a constant. So when I put this tilde, it means that there is an absolute constant such that the lower bound holds. Okay, and so this one is not a satisfying bound because this is true for every n. And in particular, it's a constant, it doesn't go to 0. And it corresponds to the risk. It's actually a trivial bound because under the boundedness assumption, I can always have a risk of 1 by just outputting the 0 function. So this is not an informative bound at all. It's a constant. It doesn't go to 0. And so basically it means that we cannot get any non-trivial bound without assumption on X if we restrict to proper procedures, so to functions which return linear functions. So we have to look at different types of procedures. And perhaps the simplest one is the one which I call truncated least squares, which basically just takes the least squares, like this, the ERM solution. But instead of returning its prediction, it will truncate the prediction between minus m and m. So if the prediction is larger than m, it will shrink it to m, and the same for minus m. So this one is improper, nonlinear, because I have truncated, so the prediction function is no longer linear, it's only piecewise linear. And there is a very classical result of Georgi and co-authors, which is really in a distribution-free setting. And it says that if we have our assumption, so this assumption on the conditional second moment, then these truncated least squares achieve a bound, which is this one. So we have this d over n, d log n over n, plus this term. And so this is it's a very remarkable result because actually there is no assumption on the distribution of x exactly as we want to. So it's a distribution-free result with our language. But on the other hand, there is a problem, which is that, at least there is an issue, which is that there is an approximation term here. So there is this additional approximation term, which means that I can only be close to the best linear function. So this excess risk can only be small when the true regression function is itself almost linear. So in a sense, only when the problem is close to being well specified or well approximated by our class. And so this is an assumption which is often fine when you do a non-parametric estimation in low dimension. But in high dimension, there is no reason to expect that your class of linear function will approximate well the true regression function. And additionally, this is also something which is not implied by our setting. We would like to approximate the best linear function in any case. So this result does not say that.
Jawad,
okay, so now I will go to our main results.
Sorry, can I ask a question? A quick question? Yeah. So if indeed, for example, the true regression function was linear, then your assumption would actually be an assumption on px, right? Because
exactly, yeah.
It would mean that x is bounded, or I mean, projection.
Yes,
of x.
it would be bounded in the direction of in the direction of the true parameter. Yeah. It would be bounded in the scalar product of wx would be bounded. Yes, you're right, exactly.
Okay, thank you.
Yeah, but I don't make this assumption, and so it can be. It doesn't have to be bounded. So yes. Okay, so now I will talk about our main results. So there are 3. And I will start. Okay, so the first one is about the same estimator as before, so truncated least squares. And okay, so this is our bound. So we have the same procedure under the same assumption, but the bound we have is closer to what we wanted. So we have a bound of an expected excess risk of order d over n. Okay, as before, this bound was distribution free. There is no assumption on the distribution of x, and it does give us a d over n bound. But also more, the important part is that we have removed the extra approximation term from the previous bound. So we don't need to assume that the true function is linear or almost linear. So this has in a way this is an important difference between the two. And there are also minor differences, which is that we have removed the log n and we have an explicit constant, but this is less important. And another thing is that the proof is actually very simple. So the proof is very elementary. It's less than 1 page. It's just some argument of leave one out argument. So you can, it's completely elementary. Whereas the original proof of the previous result was actually more involved. It's very clever, but it's also quite long. So it's a longer argument. Okay, and there is another procedure introduced by Forster-Warmuth, which achieves a similar bound as this one. But I will not talk too much about this other procedure in this talk, but it's mentioned in the paper. But I will focus on truncated least squares for now, because everything I will say about the other one is satisfied also by truncated least squares. Okay, so now we have, it can seem that we are finished. In a way, it's almost like too easy because we have just truncated the predictions, and then immediately we have exactly the bound we want. It's distribution free. It's as d over n and under our minimal assumption. But the thing is that our bound is actually a bound in expectation on the expected excess risk. And in addition to that, we could also ask for something else, which is a bound with high probability. So a high probability bound, we have to specify a confidence parameter, delta, which is a probability of failure, which will typically be small. And then you want to ask about the probability that your estimator will give an excess risk, which is small, and with probability delta. And so given delta, we can define the corresponding accuracy, which is this epsilon. And so, all right. And so this is you have like a trade-off between the accuracy and the confidence parameters. And under our assumption, there is a lower bound, which again I'm not stating, but we can. It's not too hard to show that the optimal accuracy that you can hope for is this one. So the dependence is d over n plus a logarithmic dependence on the confidence parameter. And so this is this would be ideal. So this is something that it's an exponential bound, and it's exponential because this bound is small as long as log n over this log divided by n is small. And what this means is that it's small as long as delta is not too small, and delta can be almost exponential in n. So we can have a small risk with probability almost exponential in n, the sample size. Okay, so this is what we would hope to get. And the natural question, since truncated least squares achieve the optimal bound in expectation, is whether it also has the optimal bound like with high probability. And okay, so this is what we want to know. And the answer is no. And actually, it's even worse than that. So we can show that for every n, we can find a distribution, a joint distribution of x, y, with y bounded. So it's even stronger. So it's not just the assumption is y is bounded. And the excess risk of the truncated least squares is actually completely trivial. So it's really bad. It's of constant order. So it's of order m squared, which is the same risk as the trivial zero function. And this excess risk doesn't decrease with n. So what this statement says is that with constant probability, the truncated least squares can fail with can have a constant excess risk, so a trivial performance. Okay, so it can seem like there is a contradiction between this bound in expectation, which is really nice, d over n, and this strong failure, which is a constant excess risk with constant probability. And in particular, it could seem that if you had a bound expectation, you could also get at least a bound with constant probability using Markov's inequality. But actually, this is not the case. And the reason why is that the truncated least squares is nonlinear, so it's improper. It doesn't belong to the class. It's not a linear function. And because it's nonlinear, it can actually be better than the best linear function. So actually, the excess risk can even be sometimes negative. So this variable, the excess risk, can take both positive and negative values. And so even if sometimes you can have a large excess risk, because you can also have a negative excess risk, the two can compensate in expectation. So this is a bit of an unusual behavior. Like usually when you have something that works in expectation, it tends to work with constant probability. But here this is not the case, and in a very strong sense. Like it completely fails with constant probability. Okay. Okay, so this is so what this now leaves the question, which is if there exists a procedure, which would be another one, not the truncated least squares, which achieves the optimal bound with high probability. And the answer is yes. So we have like constructed an estimator, a procedure, which achieves the optimal error bound up to a log term, but this is a bit of a detail. So the statement is that, so this is our main positive contribution, our main positive result, is that for every n and delta, there exists an estimator, a procedure f hat n, which depends on both delta, the confidence parameter, and the m, such that for every distribution without any assumption on x, and under only assumption, the conditional second moment bound, we have the bound we hope. So m squared d plus 1 log of 1 over delta over n. So this is what we wanted in the beginning. So we have a procedure which is optimal with high probability, and it's distribution free, so it doesn't require any assumption on the distribution of x. And in particular, it has to be nonlinear to achieve this, because if you stick to linear prediction functions, you cannot get any bound, as I was saying in the beginning. And it's also it's robust to heavy tails, because the only assumption is on y is this conditional second moment. So we should mention that the procedure depends on the confidence parameter delta. So it depends on the probability you want not to fail. And this dependence is actually unavoidable without stronger assumptions. So even for much simpler problems, like one parameter mean estimation, one can show that basically you cannot have a procedure which works simultaneously for every delta. And by the way, I made a mistake, so delta is not bigger than 1, it's between 0 and 1. Okay, and another important comment is that, so we have an explicit procedure, it's explicit, but it's not a practical one because it's computationally very expensive. So basically, if you want to compute it, especially in high dimension, so depends on if you want to implement it, naturally the computational complexity would be exponential in the dimension of the space. So it's not something you can really implement in practice. It's more of a theoretical result in this respect. Okay, so now I think I have to finish soon, probably. I don't know when I started exactly, but okay, so I will try to.
You have soon. 5 minutes.
Okay, thank you.
Yeah.
So I will give just some quick ideas behind the procedure. So first, there are two main sources of difficulty in our setting. The first one is our distribution-free setup. So we have no assumption on x. This is the first difficulty. And the other one is that y can be heavy-tailed. So it's not bounded, it's just this like second moment bound. So these are the two things that you have to, that they can cause difficulties. Okay, so the first step is to take the initial class of linear function and to replace it by another class by truncating all linear functions. So all linear functions, we replace them by their truncation to between minus m and m. And this is like what we did before with truncated least squares, except that before we did a truncation after computing the least square solution. And now we do it before everything. And this is actually very, very important. Okay, so when we truncate, because we have this assumption that the conditional second moment is bounded, the fact that we truncate only reduces the error, at least the risk, not the loss, but the expected loss. So truncation only reduces the risk, which is good. And there is another thing which is good, which is very important and convenient, is that it gives bounded functions. So now when you truncate the linear functions, they become bounded. But there is a price to pay, and the price to pay is that now the class of functions, of truncated linear function, becomes a non-convex class. And so, whereas the initial class was convex, because if you take two linear functions and you take the average of the two, it will still be a linear function. But if you take two truncated linear functions, the average of the two will no longer be a truncated linear function. So you moved from a convex class to a non-convex one, and this can cause some difficulties, both in terms of optimization, but also in terms of statistics. Okay, so the second step is mostly technical. So you have to use a part of the sample to construct a discretization of the space of truncated linear functions. And this is a step which is really needed for technical reasons. In particular, due to the fact that y is heavy-tailed. If y was bounded, we would not need it. But under our assumptions, it seems really needed. At least with the results we have on our disposals on optical processes. Okay, the third step is really has to do with the fact that we have a non-convex class, and if we have to have a non-convex class, there are some procedures that have been introduced, in particular in a seminal paper by Audibert, which has a very, very interesting procedure for non-convex classes. And we use this kind of idea of constructing some star-shaped domain to handle the non-convexity of the class. So this comes from this was introduced in the context of models aggregation, basically. So finite classes. Okay, so and the fourth and last step is that we have to also to recall that y is heavy-tailed. So we have to do something also with this to handle this. And so we to account for the fact that the output can be heavy-tailed, we use some robust mean estimators and some min-max procedures. And so here we were inspired by what was done by Audibert and Catoni for linear regression, and also by Lugosi and Mendelssohn, as well as Lecuyer and Leral. But I have to also to mention that these references they explicitly consider linear regression, but not in the distribution-free case, and they consider proper procedures, so they cannot give the bounds we have in our setting. Okay, and I recall that the procedure is not practical, so you cannot implement this algorithm in large dimension. Okay, so to conclude, so we have considered the problem of distribution linear regression when we make no assumption on distribution of x, and on the minimal assumption on y, which is this conditional second moment bound. So when you make no assumption on x, there is a basic obstruction, which is that no procedure which returns linear function can give you any useful bound. So you immediately have to move to different procedures. So there is this very simple truncated least squares procedure, which is very natural, and it gives an optimal d over n expected excess risk bound, which improves the classical bound on this procedure. But the problem is that it still fails with constant probability, even though it's optimal in expectation. And we have introduced a robust procedure which works in the distribution free setting and which gives the optimal high probability bound up to a log n. And also I should mention that this construction is actually, unlike the rest of the work, is not specific to the linear class. It actually extends to either finite classes or to VC classes. So basically finite dimensional classes. Okay, and as future directions, so there are things we are looking at right now. So the main direction is coming up with a more computationally implementable procedure. So this is an important thing we are looking at, and which is I think which would be really relevant. And there's also another statistical question, which is that our procedure needs the knowledge of the bound M here. And it would be nice also to try to be adaptive to not need this knowledge. And this is like, this is not easy. The typical way to do it would be Levsky's method, but in this case, we have very little control, like we have almost no assumption on Y. So it seems a bit hard. So I don't know if there is a way to do it. Okay, so this is the end of this presentation, and thank you for listening, and I'd be glad if you have questions.
Thank you very much, Jaouad. So, anyone who has questions, please open your mic. So in the meantime, maybe I'll ask with a follow-up question. Do you have any negative results if you, instead of assuming that the second moment, conditional moment of Y is bounded, if you assume that the conditional variance of Y is bounded?
Yes. So this is a very good question, and indeed, like it would seem natural that you could reckon the conditional second moment by the conditional variance, but actually this is not the case. Even actually, okay, so maybe I could share my issues. So we have a lower bound in the paper, which says that basically, even if you, so I don't know if you see the same screen as before.
We see the paper, yes, section 5.
Oh, you see the paper. Okay, great. Okay, so basically, you can show the same lower bound. In fact, even if like you have a perfect linear predictor, which implies in particular that the conditional variance is 0. So, even if the conditional second variance is 0, you still need an assumption on the conditional second moment, so it will be the conditional expectation squared, even if the conditional variance is 0, and in fact, even if the class contains a perfect predictor. So because we are really distribution free, like under this, if you make no assumption on X, you really have to pay exactly for this, like this M. So yeah. So you cannot hope to get a better dependence on the conditional distribution.
For the direction that you think you could take for the practical procedure, do you see? I mean, what is the part that is like the expensive in terms of computation?
Yes, so I can say why it's computationally expensive to implement this algorithm. Yeah. So it's for many reasons actually. The second step already is bad from a computational perspective because we discretize this set of all truncated functions, linear functions, by a finite discretization. But actually, the number of elements, the number of functions in this finite approximation is exponential in D. It's already, you already discretize by a set of size which is exponential in dimension of the order of n to the power of D. So this is already bad. And there is another reason. So even if there was not this step somehow, there would be a problem because we have truncated the linear, functions. And so now basically finding the empirical risk minimizer, so just finding the truncated linear function which has the smallest error on the data, this is a hard problem, a computationally hard, NP hard problem. And the reason why is that basically it's at least harder than the problem of finding a separating hyperplane of a cloud of points. So finding a hyperplane which separates, on which so it's harder than the problem, which is a natural problem in classification, which is separating like finding a hyperplane which contains a half space which contains a cloud of points. And this problem is hard, is known also to be hard. So even doing ERM, which is much simpler than what we do on the truncated linear class, is NP hard. So for both reasons, and actually then there are third and fourth steps, so it's a bit hidden, but they're also like you need to do a lot of things. So it's there's no hope to that. Just I don't think the true idea would be to start from this exact procedure and make it efficient, but
okay, so it's more like come up with another estimator that would maybe have like
the similar performance,
bound,
yes, exactly.
but like with similar performance, but a bit easier. Okay, I get it.
Yes.
I have a question. Can you hear me? Yes.
Yes.
Can you extend the well? You suppose that y is heavy tail, that it has a second finite moment, but can you extend to a corrupted setting where you have outliers in y? I mean, this is something that is done a lot in the robust literature. No.
Yes. So you could also consider this setting. We have not done it, so I cannot say that. So yes. So the question was about replacing the robustness to like minimal distributional assumptions to the robustness to like having like outliers, so adversarial contaminations. And I think presumably less. Yes. There may be some differences, I think. So there are, yes. So I can say that we haven't tried to do it because our point of view was try to have minimal distributional assumptions. But I agree it's a natural question. It would be like an interesting extension. Yes, I think these procedures like that I have shown tend to be robust to contaminations up to a certain contamination level, which is smaller than when the contamination level is smaller than the like the robustness, like the heavy tail term. So I think median, like this kind of technique we use are median of means, so they have some robustness to outliers, but maybe not the full bound you would hope for. But we have not tried to do it. But yeah, that would be an interesting extension, I think.
Okay, thanks.
All right. So if there are no further questions, we can call it a day.